Okay, so we can continue this with this last part with diatoms, which will be given by Agnès Bouchez and myself. I will start. What I propose you is really to show you the application of diatom biomonitoring to rivers. I will give you 3 different strategies that we develop, especially with Kalman. Again, I'm very happy you're here, Kalman. And of different kinds of indices, and I will explain you. And if I'm not able to explain, maybe I will make a sign to Kalman. Also, things about taxonomic assignation and bootstrap percentage. We will make in the second part a small summary about all the source of bias that we can have to explain the differences between microscopy and DNA. And then Agnès will present you intercalibration exercise that were carried out these last years. So let's start first with this part, diatom biomonitoring in rivers with DNA, and these 3 strategies. So the first strategy is what I call the imitation game, where there is an imitation of a calculation of an existing index, which have been developed for microscopy. So you can recognize here the workflow, the classical workflow. We sample, we look at under the microscope, we establish a taxonomic inventory, and then we calculate. So in France, it's not the IPS, but the IBD. So this is the classical way. What I showed you until now is we just bypass the microscopic identification with a molecular identification, and we just come back to the classical workflow and make a modified taxonomic inventory, which is looking like the microscopic one, and then calculate the IBD. The second strategy is to infer ecological profiles for non-assigned sequences. So the idea is a little bit hybrid. For the sequences we reach to identify, we bypass the microscopic identifications. And for the sequences we don't reach to assign, because our Diatom is not complete enough, we will infer their profile thanks to their phylogenetic neighbors. And the third approach is in fact not to identify anymore the sequences, but just to give to sequences a taxonomical profile to develop a new index, which is called the taxonomy-free index. So we are going to look at these 3 strategies one by one, and I will explain you when it's better to use one or the other. So let's start with the first one. So the one that you already saw for Mayotte. So I repeat. So we have a floristic list with DNA. We transform it with this correction factor to have a, let's say, modified floristic list, which should look like to the microscopic one. So you remember that? Is it okay? Yeah. And here is the floristic list with DNA. So you can see that we have a similar floristic list. So the application to France is with IBD. So the IBD, we have 828 taxa with an ecological profile. So you can see here some example of ecological profiles. And we carried out some tests on different campaigns, which were carried out by the water agencies. And in fact, the laboratories sent to us the samplings. So one part was for microscopy and the other part was for DNA, and we did the DNA. You can see here we had 658 sites. You see the position in France. In fact, we wanted to have some long rivers. This is the longest river here. It's the Loire River, but also others here. And also some areas with, let's say, all the network. We wanted to have these 2 strategies. And here are the results. So here, this is the diatom index in microscopy. It's from 1 to 20. So 1 is bad water quality, 20 is very good water quality. So microscopy, horizontal axis, and vertical axis is the molecular index. So you can see that there is a good correlation, and this has been here it was identified with the version 7 of Diatom. But versions after versions, we improved the number of species that we were able to identify. 74% of correlation between microscopy and DNA. So pretty high correlation. Yes, and so the improvement of the correlation was thanks to that barcode completion. And yes, what is important to see is that also the slope is almost 1:1 here. So it's 0.9, but we are not far from 1. So it's a good point also. And here, what I would like to show you is the completion again of DIAD barcode in different regions of France. So here it's mainland France. So Europe, let's say Europe, continental Europe. So we have 90% of the completions of the sequences. French Guiana, you see, only 35%. The French Indies, the West Indies here, Guadeloupe and Martinique near Cuba, 80%, something like 80%. And Mayotte, so this island we worked quite intensively, 60%. And Réunion, it's in the middle of the ocean, 90%, so good score. So you can imagine that we are okay to use the IBD in this situation when we have a very good completion of DIAD barcode. But what can we do in this situation when we have only 35% or only 60%, and when we have, let's say, 80%? And so I'm going to show you that the next strategies are interesting to do that. But to sum up, the method of just bypassing this imitation game is good when you have a good reference library, which is almost complete. Let's talk about this strategy. Let's say the hybrid strategy. So we start with a list of sequences. So we have our Data2 pipeline. We have the list of sequences here, and we try to assign them a name. So some of the sequences we reach to give them a name. So we can establish a floristic list thanks to DIAD barcode. And then for this species, you know the ecological profile, so you can calculate a Diatom index. But some of them, let's say 20% of them, you don't reach to give them a name because DIAD barcode is not complete enough. So there is a loss of information. And the idea is these lost, let's say lost sequences, the idea is to infer them into the Diatom phylogeny. So for instance, it will be these red unknown, these red sequences. So we make a phylogenetic insertion in the Diatom phylogeny, and we assess their ecological profile thanks to the ecological profiles of the neighbors. So what you can see here, these black bars are in fact the ecology of a species. So if you are on the left, it's a bad water quality. If you are on the right, it's a good water quality. If your red sequence, so the unknown sequence is here, in the middle of two sequences where there are good water quality, there is good chance that it's also a good water quality species. So you can infer like that the ecology. But the question is there a phylogenetic signal of the ecological profile of diatoms? So we tested that. So this was the work of François Keck. What he did, he made a phylogeny of diatoms. Here, this is a circular tree. So you have a phylogeny of diatoms, and he looked at the ecology of each species. So these are, in fact, the IPS profiles. And you can see that there are some clades. Most of the clades, in fact, the ecology is the same. So it means that there is, in fact, a phylogenetic signal of the ecology of diatoms. It's not random. You can see clearly that there are some patch. So we come back to our test. What did François? He inserted the environmental sequences in this phylogeny, and he was able to define their ecology thanks to their neighbors. This is the classical Diatom index, so without taking into account these lost sequences, and this is the improvement. And he was able to improve by, so here this is the correlations, 7%, so a good improvement. And the differences between microscopy and DNA was also reduced by, let's say, 30%. So here you have microscopy, and here you have, let's say, the phylogenetic inference Diatom index, so this mixed index. So good result. So to sum up, this method takes advantage of 100% of the data, of the DNA data. It improves the estimation of Diatom indices compared to classical approach. It's based on a solid or robust theoretical foundation based on the Darwinian principles, and it's built on existing database and indices. And we can consider that this method as a transition between de novo molecules, such as taxonomy-free indices I'm going to show you just after, or provide machine learning indices. So let's go now to this last approach, this taxonomy-free approach. And this has been really the work of Kalman. So let's start again with these environmental sequences coming from the pipeline. And again, you have a loss of information because the reference database is not complete enough. The idea is, if we are not able to identify all these sequences, let's forget it, and let's give to each sequence an ecological profile. So as it has been done for the IPS or whatever. But for this, of course, you need training data with physicochemical chemistry and also the DNA data. And we develop a new index based based only on the sequence profiles. And what Kalman did, he did 4 different indices based on this training data. In fact, he developed a new index based on the morphological species. So a classical IPS based on morpho species. A second one based on OTU. So OTUs, remember, it's our groups of sequences which are similar. And here the percentage of similarity chosen was 95%. A second one based on ISU. So ISU, I will show you, it's before OTU. And the last one based on ISV. So these are the sequences, the denoise sequences that we get from DADA2 pipeline. How did we how did we develop these 4 different indices? So he had a training data set. He had a data set. He divided this data set into 2 parts. One for the training. So the training is to develop these environmental gradients, so it's to define this ecological profile for each morphological species, or each OTU, or each ISV, and a test data set, so really a naive data set where we can apply these new indices. And then he compared all that. He compared that to the pollution that we could find in the river. Yes, just to explain you a little bit how is working Mover and the OTUs. You start from raw sequences. There is a first filter on the length, bad quality, removed. And then if you have a sequence which is repeated several times, you say, okay, this sequence, I found it 1,000 times in this sample. So this is what we call dereplication. And then, I don't know if you remember, sometimes you can have some chimera. So chimera are, you start sequencing one species, and then the PCR, there is a problem. you continue with a second species. So chimeras are when you have a lion or an elephant. All this is not reality. So you have to remove this chimera, and then you make a designation of this species. And so you can use, I don't remember the percentage you use, Kalman, here, if it's 80% or whatever, doesn't matter. So you use a taxonomic, you make a taxonomic assignation with 80%, for instance. And then this ISU, you may still have some mistakes. You can group together into what we call an OTU with a certain percentage. And then since in an OTU you can have several sequences, you have to check if each sequence belongs to the same species. And so again here, you make a taxonomic assignation based on a certain threshold. And then you get your molecular inventory. Is it clear? Okay. So he made these different indices based on morphological data, OTU, ISU, ISV. Here are the results. So what you can see here on the horizontal axis, each horizontal axis is in fact the pollution gradient. It's based on nutrients and organic matter. It's a mixture of that. And on the vertical axis here, you have the index. You have the index for morphospecies, for OTU, for ISV, so data2, and ESU. And what is surprising is for each index, you have quite good correlations for morphospecies. So in fact, you have good correlation. The only one which is not very good is the OTU index, 76%, whereas the others are 84%. First surprise of Kalman, why does the ISU, so the non-denoised index, work? Because you remember, so when you have all these sequences, maybe some are sequencing mistakes, and to take into account that, you make OTUs, or you remove that when you make data2 and ISV. So the hypothesis is that these sequencing mistakes, so there are probably sequencing errors, but maybe when we define their profiles is looking like the mother sequence, let's say the real sequence. And so this is probably why it's working. And this question the needs for denoising for biomonitoring purpose. Okay. The second question is why does the OTU index work less well than the other indices? And the hypothesis is that sometimes OTU, okay, they are good. There are really some nice species, true species, like this one, where you have a nice ecological profile. So probably here it's a meaningful OTU with sequences which are really from the same species and so the same ecology. But maybe sometimes, and this is the case here, it's true data, it's mixing some species which have not exactly the same ecology. And you can imagine that here probably there is one species here, maybe a second one here, and a third one here. And then when you calculate the ecological profile and the sensitivity value, sometimes it's okay. Here it's not a problem, but here for this OTU, the sensitivity is not corresponding to the reality, and maybe there are 3 species, and when you calculate the sensitivity value, it's different from the real optimum. So to sum up, taxonomy-free approaches work well, provided that you have some chemical data for the training that data. OTU clustering can hide important ecological information. And yes, the idea of doing without clustering and even denoising, the idea behind was, so you saw that we made some standardization for sampling, how to preserve samples. We made a standard. We made a standard for the barcoding library. But at one day, we will have also to standardize the bioinformatic pipeline. And the idea was to have the minimal things to standardize and not to have a too complex standard. And the idea was, can we try to to simplify the bioinformatic pipeline in order to have simple standard. And this was the idea of using, of trying with ISU without denoising. So to conclude, we come back to the real situation, what we have in the field in France. In the case we have a reference database with a good completion, we can use classical Diatom indices. In the case, for instance, of French Guiana, where we don't know the taxonomy, less than 50% of the sequences we know this, we can assign them a name. Let's forget the taxonomy and let's go for taxonomy free. And when we are in between, so for instance, these French islands, Guadeloupe and Martinique, maybe the best solution would be to have this mixture and this hybrid index where we make some phylogenetic assignation. Okay, and do you have questions on these three strategies? Little bit heavy. Don't hesitate if you don't understand things. If not, but I'm looking, I'm too late maybe? No, it's okay? No? What time shall we stop? I don't know. At 12? Okay. No, but maybe we can skip this. Okay, so I skip this one. Okay. Maybe we can go directly to the source of bias. Just to sum up a little bit. Yes, it's really when you compare a microscopic list to a DNA list, even if you make this transformation with the biovolumes and the correction factors, sometimes you don't have the same floristic list. So I would like just to give you these thoughts on the if you want to compare this list, you have to think about first about the physiological status of your cells. You know, when you are counting diatoms, we count dead fructules. So maybe if you have this floristic list again, some cells like this one is Amphora pediculus is dead, and maybe Achnanthidium minutissimum is so. I mean, the community is not so healthy, and maybe let's say 50% of the cells of Achnanthidium minutissimum are empty cells. So you just need to think about that. But maybe the picture that you have with microscopy won't be the same simply because of the physiological status of your community. Second, bias. So I think you understood. If you have a reference database which is not complete, you're not able to identify and to detect the species. So again, if let's imagine Achnanthidium minutissimum won't be able to identify it, and so the floristic list will be different from the microscopy. Easy. Think also about neighbor species. Let's imagine we have in microscopy Ancionema minutum, and with the Diatom it's identified in Ancionema silesiacum. Maybe these are, and I can tell you it's the same. It's the same taxon, but is not identified probably in the same way with microscopy and DNA. Navicula cryptotenella, Cryptodenoides, maybe they are the same species. And that's all. Do you have questions about the bias? But we can think about other bias, of course. No other questions? So we can move to you, Agnes, maybe? Okay.
So after these taxonomy-free, maybe a bit more complicated things, I will go back to very practical things. That will be a way to be cooler. Okay. Oh yes. Sorry. Okay, so I want to present you what we call the ring test. That was an interlaboratory test that was done in the context of this network, the Aquanet, that Frédéric introduced you, and to compare different wet lab protocols of Diatom metabarcoding in view of future standardization. In fact, we take the opportunity of this large network to advance things like that, because it's difficult to find fundings for this kind of exercise. And we had some more or less fundings and also some people willing to take part. So we tried to manage that. So this was led by Cécile Chardon. She is the technician in charge of our molecular lab, and by Valentin Vasselon, who was one of our former PhD student at the same time as Kalman, and now he's in a private company, Simabio. What we could see that we had, Frédéric told you about standards about the sample preservation and sample collection, about the barcode library completion and how it's composed, but we had nothing about DNA extraction, and also we have nothing about barcode amplification for this metabarcoding process. So we wanted to look a bit better in the different protocols and how different lab could obtain same results with the same protocol. So we gathered 17 participants that were either from public laboratories or from private offices. And there were some beginners, there were some advanced people that were taking part in this exercise. And we in RAE were the reference laboratory, sorry. Okay, and I think Kalman, you were one of the participants. Yeah. So for this exercise, we had one set of controlled samples. What I mean by controlled samples, we had 2 environmental samples, one from lake and one from river. And in fact, when I say controlled, it's because we know them very well. We have analyzed them and we know the place. We know they are really much controlled environmental samples. And we had also 2, let's say, artificial samples. One was a synthetic community. We asked a company to synthesize the barcode for different species. So we had the exact barcode of the species because it was a molecule that has been synthesized. And we had a mix of different species that has their synthesized barcode. And we had also a mock community. That means that we mixed DNA from different strains, and we knew which were the strains that were inside the mock community. Okay, so we have these 4 samples, and we targeted the 2 steps, as I said previously, so DNA extraction and barcode PCR barcode amplification. So we had 2 kinds of approaches. One was the one for all, that means one protocol that may be transferred to different labs. So one protocol for all labs. And that I will present you here the results for the PCR. We use one Taq polymerase and one barcode. Everybody had the same protocol that was clearly defined and transferred to everybody. And with the 4 DNA extracts, each lab received a set of the 4 DNA extracts that were prepared by our lab. And each of the 17 laboratories made 1 PCR per sample. So, and in our lab, we made 3 PCR per sample because we were the reference lab. And then the participants sent back the PCR products to our lab. And we, as reference laboratory, we prepared the library for the sequencing. We send them to sequencing platforms, and we did the bioinformatics. The other strategy was the all-for-one. That means everybody use his favorite protocol, and to try to analyze the same samples to see if there are big variation among protocols and among labs and so on. And I will present that for DNA extraction. So the two environmental samples, of course, the mock communities were already extracted, and synthetic community also. We had directly DNA, so we could not do that with these samples, but we had the two environmental samples that were sent. Aliquots were sent to all participants wishing to take part. So here we had only 9 participants, because the ones that were not used to it, they don't have any previous protocols. So here we had only the participants that were more advanced, and they made 3 DNA extractions per sample. And we did the same, 3 DNA extractions per sample. Then the DNA extracts were sent back to us, and we proceeded with PCR, sequencing library preparation, and bioinformatics in the same way for all the samples. So let's have a look at the results. So for the one-for-all protocol transfer, so that when we everybody use the same protocol for PCR with 4 DNA extracts. Here, what you can see is the composition of the mock community. So here, the 3 first bars stands for what we did in the reference library, the 3 PCR per sample. And here, each bar is 1 participant. And you can see here that for the mock community, it's quite homogeneous. And also the mock community, we did it as a gradient of different concentration of the different species that were included in it. So you can see that is one species that is more represented than the others. And we had also some that are very, very slight and difficult to find. And we can see that the proportions are good among all partners. And for the synthetic community, that was a bit more complex. And you can see also that proportions are good, and that the composition also is good. So it was quite homogeneous between participants for these 2 samples. When we look now at the river sample here on the left, and the lake sample on the right, you can see again that it's quite similar. And even if some labs have been doing that for the first time, we could see very good results. Of course, there's this sample that was quite different because there was a mix of samples. So that was not because of the protocol, but that was an error of the participant. So we could see here that the protocol is easily transferable, labs being advanced or not advanced. Now let's look at the results of the all-for-one for DNA extraction. So again, every participant has 2 environmental samples, the river and the lake sample. And they did 3 DNA extraction per sample with their favorite DNA extraction method. So you can see here the list of the different DNA extraction per participants. So we use as reference laboratory, we use the one that we already showed you yesterday. And some used the same here, but with a different machine. And also, you can see there is a variety of way to do. Some did Genelute, homemade, and the others used kits. So here, if you look at the river sample on the top, you could see that the composition is not very different from one lab to the other. Here you can see that it goes by 3 because we did three DNA extraction per participant. So you can see that each participant has very consistent results, but they differed slightly, but in fact not so much. And for Lake, it was about the same. It differed also a little bit, but similar species were detected. And we have some variability on relative abundances, you can see. So that's changes in species percentage, but not so bad. If we look a bit deeper on that, what we can see that the variability in the species percentage was due to the lab, of course. You could see that on the previous slide, but also maybe it's more a bit linked also to the lysis step of the DNA extraction method. For example, here in blue, you have those who had no lysis step, while you have here those using RNase or proteinase K or both. And so it seems that the lysis step, so we didn't went very far on that, but probably has some importance. But what's interesting, it was comes next. So here, for river, on the top, you have the IPS value. So it's the index that Frédéric showed you. And you have the different participants. And you can see the box plot, which figures the 3 replicates of DNA extraction. And so from these floristic inventories, we calculated IPS values. And you can see that so each participant have 3 replicates that are quite similar, even very similar here, here, and here. Here it's for us, reference lab. And we put this line at the median for all the results. And you can see that all the results are not far from 17, which is the value for IPS, the mean value. And it's the highest point here is not even 18, and the lowest point is not is 16.8. So you can see that it's really in a short range and a limited range, and so it's quite good. And if you look at the lake sample, it's about the same. It's between 15.1 and 16.4. So there is really no impact. We also did that on the IBD, and there was no impact of the percentage of the species percentage changes. And there is a really moderate impact on IPS. So we are very confident with this kind of all for one. That means that overall the methodology is quite robust, and we had the same. We did the same for the PCR, and we obtained the same kind of results. That was even if people use different PCR machine, Taq polymerase, and so on. In the end, when it comes to produce ecological indices, then it's quite good. Everybody has about the same result. So that was really the idea that all protocols can be used and to transfer a protocol to even either advanced or naive participants. So that's good news for the implementation of these methods. And so I want, of course, to thank all participants. And there is a paper that should come soon, hopefully, but still some work to do. Okay, so now I'm ready for questions, if you want. So we are just in time. Oh, okay. So maybe if you have questions for that, or from what Frédéric said this morning, so do not hesitate, but maybe it's a lot already, yes?
Okay, it's not really a question, it's more like a comment regarding the listing that we saw. I'm really glad that someone finally pointed out that it really doesn't matter which kit is someone using or which PCR machine is used, because even before you pointed out that there will be a paperwork for this, I really consider this as a contribution to the science for itself, regardless what is done with what was the goal of investigation. Because we all know how many kits are available and how many PCR machines are available, and we all know how different prices they have. So I really hope that we will have more paperworks like this, and no matter if that comes from metabarcoding or anything else done by molecular methods. That's what I wanted to say.
Thank you.
And thank you, actually.
In fact, I have to say that it's really this kind of study, as you pointed, it's interesting for science, but it's difficult to have it funded. And so we had some money that was staying from a previous project that we could mobilize for that. And also because everybody wished to participate. So that was great. And I think we need this kind of exercise really to give a way to standardization, so that standardization is not so strict, because the results show that. So I hope it will be a good step towards standardization, towards quite open standardization.
Ako ima još pitanja, slobodno, nemojte se ustručavati. Ovo je jedinstvena prilika. Okay, to switch in English. Okay. Don't hesitate to ask. This is the unique opportunity to, in how to say, in vivo, ask our presenters, who are, as you can see, experts bringing these standards into the practice on the European Union level and wider.
Especially, are you ready to answer to the questions of the evaluation tomorrow about taxonomy free, for example? No, but please, even when we are at lunch or coffee breaks, do not hesitate to come to us and discuss. And even later, if you have any questions, we will give our emails. And